recap what all we have by this point, we know about basic measurements, derived measurements, Aristotelian and Galilean theories of physics. We have found how you would solve those in terms of thinking about the motion as sequences of numbers. And then using that theory, we have confirmed Galilean physics and rejected Aristotelian, and we have some equations that predict motion under freefall. Now, in this video, I'll talk about Newtonian physics, the second law of motion, and indicate how the solutions that we have so far are not really adequate for all of the things that we want to do with them, and eventually start looking at secant lines and sequences of secant lines that build up to talking about tangent lines. So, Newtonian physics. Well, of course, we can't analyze yet motion that is not just governed by constant force, right? If you have a varying force and therefore a varying acceleration, we don't yet know how to analyze that motion. For another thing, there is this weird feature that objects tend to fall harder when they're more massive, and yet they fall at the same speed and acceleration. How can we explain this with the theory developed so far? Well, given that force is proportionate to acceleration and gravity exerts for heavy objects a heavier force, then we might think that the exact equation, not just the sort of relationship from one to the other, but in fact the true equality involves mass. And for another thing, if we just hypothesize this very simple equation and think about what it would mean, well, one implication of this equation is that very massive objects would require a very large force in order to get them to accelerate, which makes perfect sense. So in fact, this equation makes good sense, and you see how the mass can increase, and the force would therefore increase, all while the acceleration staying constant, right? So imagine that you had a mass of, mass units are typically in kilograms, so suppose that you had a mass of 1 kilogram and it accelerates at the, acceleration due to gravity. That's going to determine a certain amount of gravitational force that it experiences. If you double the mass but keep the acceleration constant, you'll have a larger gravitational force that this thing exerts, and yet the acceleration will be the same. So all of that confirms what we can empirically discover, and so it seems to be a good law. Now, what do we do about this fact that we cannot analyze other motion quite so easily? Well, let's take another approach. We know that there are these relationships between displacement, velocity, and acceleration. We know that average velocity is delta x over delta t, and that gets us an approximation of the velocity over a time interval. If we choose a smaller time interval, we get a better approximation. And one way to visualize this is to actually plot a function and a bunch of secant lines. Because whenever we do this, it turns out that we are finding the slope of a certain secant line. So let's take, for instance, this function, and I'll go ahead and print that function. I'll try to get rid of the rest of this real quick so that we can focus on one thing at a time. And this is the function that we're talking about right now. So this confusing mess, t cosine cubed minus blah, blah, blah. Now, let's go ahead and plot this function. And if we imagine that this is the function that governs the motion of some object, right? So the object starts off not at 0, but close to it, goes in the positive direction for a while, then descends, swoops down, turns around, And keep in mind that this is the time axis and this is the displacement axis. So if we picked a particular point in time, let's say the time equal to 3, then we would be looking at a point on this graph. So it would be this point, right? When time is equal to 3, the displacement seems to be about -3. So, so what if we want to know what the velocity of the particle is in the vicinity of this point? Well, if we found some other future time, like let's say time is equal to 4, and we compute its displacement, that's typically how we would find the average velocity over a time interval. And graphically, that would mean that we're locating this other point, and when we find delta x, we're finding the rise in the function. When we find delta t, we're finding the run. And delta x over delta t is rise over run, so it's the slope of the line that connects these 2 points. So let's go ahead and get a depiction of that. So here's a depiction of exactly what we were just talking about, right? We have the point where time is equal to 3. We have the point where time is equal to 4. We find the corresponding x coordinates and draw the line through them. The average velocity will be the slope of this line. We can get a better approximation of the velocity close to 3, right? That's our focus, is finding the velocity close to this point. This is a bad approximation because you can see that all kinds of stuff is going on in between. But if we shrink the time interval to, let's say, 3.5, then we get a better approximation. So now I'm evaluating at 3.5, closer to the function and probably a little bit more accurate as far as what the true velocity of this particle is at that moment. Now let's shrink the time interval a little bit more, and you get an even better approximation, and we can keep going. And as we do so, we get better and better approximations. Each one of these is a secant line, but as we do this, we get closer and closer to what's called the tangent line. Now, you might have heard of the tangent line from geometry class. The tangent line for a circle is the line that crosses through precisely one point of the circle. So, may look like, for instance, this. Now, in geometry, the important lesson was that the tangent line always passes through at a right angle to the radius. That doesn't actually matter for our purposes right now. But that's the idea of the tangent line for circles, and that's similar to the idea of a tangent line here for this curve. The tangent line will be the line that passes through exactly one point in the vicinity of, in this case, 3, where time is equal to 3, it'll pass through just this one point. So to speak, it'll just barely kiss the function. And the slope of the tangent line is what we call the velocity, right? That's the true, precise, accurate velocity, whereas all of these average velocities are approximations of that.